The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to today's webinar. Today we're going to talk about mastering the art of dissolved air flotation operation. My name is Ryan Kumpula and I am the industry manager for Brenntag Pacific. Today I am going to introduce Kevin Cope, who will be presenting this webinar. Kevin Cope started his career back in the late 70s at Triolite with a wastewater focus and did a lot of work with IAF and DAF and specialized in those areas. Throughout his career, he's worked for a variety of different water treatment companies, including Dearborn and Calgon, and before joining Brenntag, was a product manager with Camira. Now, Kevin is the business development application specialist for Brenntag North America and lives in Pittsburgh, Pennsylvania. He also serves currently on the Association of Water Technologies board and has participated as a wastewater technical trainer for several years with AWT. In Kevin's personal life, he's an artist and has been married to his wife, Ruth, for 39 years. In the picture up to the right there, you can see Kevin standing next to a painting he put together for last year's Association of Water Treaters conference in Grand Rapids, Michigan. And that was given away as part of a charity, so we appreciate the work that Kevin does, and it helps spread the word of charity throughout North America. Kevin, go ahead.
Ryan, thank you. I very much appreciate the introduction. I'd like to welcome everyone to our webinar today. You'll notice in the top right-hand corner or somewhere within your screen, you will notice a small orange arrow. If you press that arrow, it'll expand, and you'll see something that looks very similar to this. You can type in any question you have down here in the box, then hit submit or send, and we will get that, and we will try to answer your questions accordingly. The ones we don't get to today, we will answer via emails or calls, whatever you prefer. So I'd like to begin the webinar. Oh, I'm sorry. Then to minimize, simply click the minimization screen, and it'll go away, and that'll be off your screen. So in the past, Brenntag has really been committed to helping our customers and prospects to understand the different aspects of the water treatment industry. And to date, we've conducted a number of webinars: heavy metals removal, anti-scalants, oily waste treatment, foam control, which we did in association with the AWT, Association of Water Technologies. We've done coagulation flocculation, successful jar testing, successful plant trial, and also removal of chelators and non-chelators from industrial waste water streams, and also successful biological treatment. So these are some of the webinars that we've conducted in the past. But today's webinar is entitled Mastering the Art of DAF Flotation, or Dissolved Air Flotation Operation. So some of the subjects we'd like to talk about today are definition, operation, basic concepts, basic designs, chemical treatment, chemical feed and mixing, float removal, operational controls, troubleshooting, maintenance, and finish up with any questions that may come up. So let's start out with a definition. I got this directly from Wikipedia, and I thought it was very, very well done. Dissolved air flotation, or DAF or DAFs, is a water treatment process that clarifies wastewater or other waters by the removal of suspended matter such as oil or solids. The removal is achieved by dissolving air in water or wastewater under pressure and then releasing the air at atmospheric pressure in a flotation tank. The released air forms tiny bubbles that adhere to the suspended matter, causing the suspended material to float to the surface of the water, where it may be removed by a skimming device. So when we were putting this together, we were kind of joking around that DAF also can stand for doesn't always float. And it reminded me of an application very early on in my career where I was actually called to go into a bowling ball manufacturer who was having problems with a DAF unit. And one of the final steps in manufacturing of bowling balls is to polish the bowling balls. And when they polish it, they get fine particles that come off, and they run that water through a DAF unit, cleaning the water, and then bringing the water back in as a recycle. Well, over the years, you can kind of well imagine, we started seeing small little chips of bowling balls coming into the DAF, which just frankly would not float. And over the years, they basically filled the DAF unit up and actually turned off the bottom drain of their DAF. So when I got there, they really only had 1 to 2 feet of clear water on the top of the DAF, and it was an absolute mess. So it reminded me when we were joking around about DAFs standing for doesn't always float. Reminded me of my DAF unit at a bowling ball manufacturer. So I want to talk about the types of flotations that are on the market. We have dissolved air flotation, which we're going to focus on today, DAF. And this picture on the right clearly shows very nicely what the water in a DAF should look like. The water should look white, and I liken it to when you go to the kitchen in the summer and turn on your spigot, and you get the white water in your system, and that's air being dissolved in the water. So very, very fine particles of air, very fine air droplets that rise to the top. Some of the newer operations is called cavitated air flotation, or CAFs. In there we see direct air injection. Can also use an air aspirator, and it creates what are called micro bubbles. And these two pictures here, I think, do a very nice job of clearly showing the difference between the air in a dissolved air flotation and the air in a CAF unit. And then lastly, we have what's called an induced air flotation, IAF, or an induced gas flotation. The gas flotation, those are systems that are used primarily in any air where there's potential for explosions or flammable conditions. I've only ever seen one GAF in my career. But this slide here, I think, is very effective to show the difference in the bubble sizes between a DAF, CAF, and IAF. Clearly a major difference in the size of the bubbles. So I put this photo in just basically to show what an IAF looks like. This is a picture I took down in Texas many, many years ago. And they have what's called an impeller or a depurator that spins very, very rapidly. And this spinning creates a vortex which sucks air. And here's a good depiction of what happens. Here we see the motor and the depurator which spins. The air is sucked down, and the depurator, creating a vortex, sucks the air down. There's a hood here with openings in it to break the air bubbles up. The air then comes to the top, taking with it any of the oil or contaminants, and then it's skimmed off into some kind of a discharge trough. But that's typically what an IAF unit looks like. So if we talk about the operation, for DAFs, wastewater is mixed with water, which has been pressurized with air. The air is dissolved in the water under pressure. In the skim tank, usually through a pressure release valve, the pressure drops, allowing the air to come out of solution, forming microbubbles. In the skim tank, the waste floats, and in the unit, some of the solids may sink to the bottom. Microbubbles of air attach to the flock, causing them to become buoyant and rise. A float layer is formed at the water's surface. The water drains out of the float, and the sludge is skimmed off. These air bubbles may precipitate on the surface of the solids, attach to the solids, and or become entrapped into the flock as it is formed. The resulting mass is buoyant and quickly rises. The resulting mass is buoyant and quickly rises to the surface. Now, I am an artist, so I couldn't help but to put a little pictorial in, just kind of showing the rise of the bubbles and the pin flock in the flock to the top of the unit. This next slide, I think, is very helpful understanding the rise of air in a DAF unit. Here we see, again, we talked about the spigot, the faucet in your kitchen in the summer, and how there's air entrapped in the water. This air now will rise very slowly, bringing the particles of oil or particles to the top of the DAF unit. So I think this is really a great picture showing exactly what the DAF airflow should look like coming to the top. every DAF system has basically three units: a pressurization tank, a pressure release valve, and a skim tank. The pressurization tank is a tank that water and air are mixed together under pressure. Usually there's fill inside of the pressurization tanks that allows for the air and water to mix better. Very similar to the fill in a cooling tower, where the water hits the fill, breaks into smaller particle droplets, allows for better evaporation, thereby a better heat transfer or loss of heat through evaporation. The fill in the pressurization tanks are basically the same. There's usually a pressure gauge to control the amount of air. There's a level control to prevent any burping, and we'll go through burping later. And usually there's a sight gauge. I shouldn't say usually. Oftentimes there's a sight gauge. And I very much like the sight gauge on the side of the tanks to really get an idea of where the level in the pressurization tank is at. They always have a pressure release valve. It's a valve that's basically there to release the air and water mixture. Upon releasing the air-water mixture, the dissolved air separates from the water. You can also control the pressure with the pressure release valve. Then they have a skim tank, which can either be circular or rectangular. There, in the skim tank, the separation occurs where the skim will come to the top. The solids will float. The skim or solids are removed using a mechanism of some sort. Sometimes there is a bottom removal system where the solids will settle to the bottom. Not always, but often there will be a bottom removal system. And then this also sometimes can be called the float tank in a DAF. So there's three types of DAF units: recycle stream pressurization, full stream pressurization, and partial stream pressurization. And we'll go through each of these to get a basic understanding of how each works. So if we look at the recycle stream pressurization, we have wastewater that comes into the facility, into the plant, through the skim tank, and then is discharged as clean water. In a recycle system, clean water will be brought back through and put into the pressurization tank, where it is mixed with air, creating a saturation of air and water together. This air and water mixture now will go down and be released through the pressurization tank, where the air is now released, and there it will be mixed with the waste stream coming in. Once it gets into the skim tank, the air will be released, the air will rise. As it's rising, it will bring solids to the top of the tank, where the skim or scum or float is removed from the top of the DAF unit. There's also what's called a full stream pressurization tank. And here, very similar to the partial stream DAF, the waste stream comes in, but in this case, the entire stream is pressurized with air. Again, now releasing through a pressure release valve, and the float now comes to the top and is skimmed off. I'm not a big fan of these units, and the reason being is because you're pressurizing the incoming waste water, this tank can oftentimes become fouled, causing problems with good air-water mixture, but just causing some real basic problems with making this a very dirty tank. But this is a fairly common full-stream pressurization unit. Another unit is called a partial stream pressurization, very similar to the recycle, but instead of recycling clean water, here we are taking a partial part of the stream through the pressurization tank, through the pressure release valve, and then into the skim tank. But here you have the same basic problems with this tank becoming fouled with contaminants and causing some basic operational problems. I put this picture in just basically to show that some of the newer designs, we're starting to see them incorporate the use of parallel plates, very similar to the lamellas, which makes for a better separation through the unit, better solids removal. So these are some of the new designs that we're starting to see, the use of parallel plates within a DAF unit. So let's talk a little bit about chemical treatment. And I think these are very, very key. We have precipitation. These are the three components of chemical treatment. Precipitation. The production or formation of a chemical precipitant. To precipitate from soluble to insoluble. This is a great picture showing where this is soluble material. Some mechanism, either a pH or metal precipitant, was used, and we've taken and brought that from soluble to insoluble. The next step we have is coagulation, also known as charge neutralization, pin flock creation, or break-in and emulsion. And if you look very closely along the shaft of the jar stirrer, you will see the very, very small pin flock that is beginning to form. And then the last step is known as flocculation, also called pin flock bridging or pin flock building. And here you'll see that we've created larger particle sizes. So this is the third step in the chemical treatment known as flocculation. Now these are really key things to understand. Precipitation must occur fully before coagulation. If not, none of the soluble material will then be able to be taken out through a DAF unit. So precipitation must occur fully before the coagulation step. Moving further, coagulation must fully occur before flocculation. If you don't see this, you can have pin flock carrying through the DAF unit, or in some severe cases, actually have post-treatment coagulation where the products will start working after the DAF unit. And then lastly, we have flocculation, which is the final step, which increases flock size, can entrap air, and will float the sludge. So now let's talk a little bit about testing. The real tried and true method of testing a DAF unit is the use of a jar stirrer. Here we see a portable jar stirrer, a 4-gang jar stirrer, and I showed earlier on the coagulation, you were looking right in this area, and these are what the paddles look like in a filled four-station gang stirrer. This is typically used in a laboratory. If you look very closely, you can see the pin flocks starting to grow here in the lab version of a jar stirrer. So when we were developing this, putting this presentation together, a lot of us were kind of joking around about some people saying, I only like DAFs when the flux rises to the top. And I will say that I have seen a few times when the material tends to sink, but a DAF unit, because the materials tends to be fairly light and fluffy, can be taken out very adequately in a DAF unit. And back to my story about the bowling balls, I don't think bowling ball waste is really conducive to use in a DAF unit. But I always like to use a little joke and say, as long as it doesn't break the bottom of the beaker, you might be okay. But, when you start getting the very, very dense flock and it's really sinking very rapidly to the bottom, a DAF unit may not be the best choice of pieces of equipment. And again, I always like to joke around and say, make sure you don't break the bottom of the beaker when you're running your tests. Another good little trick that we use is the use of Alka-Seltzer tablets. What I find is, once the jar testing is done, pop an Alka-Seltzer tablet in and see how the air comes to the top, how it'll bring the sludge to the top. It's a good little trick to make sure that the stuff in the flock will indeed rise for you. Another good thing to consider is an air stone. A little aquarium air pump is sitting here, and a clear graduated cylinder, some aquarium tubing, and an air stone. And can give you basically the same effect, can help you look and see how well the flock will rise to the top after you've flocculated it. The other thing that's really nice about this piece of equipment, it can be used very nicely to test defoamers or anti-foams. So it can serve two purposes, checking out for a DAF, but then also helping you out if you're testing or having foaming issues and you want to test foaming issues. And I actually forgot about this when I was putting this together, just remembered about a day or so ago. But another idea is to take a tap off the recycle line. A lot of times, that if there is a tap, you have the air and water mixed together, which you take a little tap off of that and use it in your jar, bring a jar beaker over, put a little bit in, and see how well that rises or causes the flock to rise to the top. So let's talk a little bit about chemical feed and mixing. Here we have a typical system. We have the pressurization tank, we have the skim tank, And right down here is the pressure release tank. So the water comes through here into the DAF, the skim tank. This is the pressurization tank. And in this area is where the pressure release valve and the two are mixed together and come into the DAF. In this case, they're feeding the coagulant into the second cell. First cell is used for pH adjustment of some sort. Feeding coagulation. Coagulation occurs. Then you have flocculation, which occurs, and then into the DAF unit. So a pretty typical design of a DAF system. Now, these are fairly new, and I've been in this industry 40 years, so fairly new means they've probably been around 30 years. But basically what these are what are called serpentine coils, and they do a nice job of giving you ample mixing prior to your DAF unit. The other really nice thing about this is it gives you a variety of locations where you can feed your coagulant, your flocculant, or switch out where you want to add your air-water mixture. So again, it gives you a number of different opportunities to play around and really making your system run as efficiently as possible with all the different locations where you can feed chemical or feed your dissolved air and water mixture. The last was a horizontal serpentine coil. This is a vertical design, goes up and down, but basically the same setup as the horizontal. This was a picture from one of my coworkers. I've never seen one of these. I've worked primarily on the horizontal units. Now let's talk a little bit about float removal. This is a circular DAF unit. In this case, the skimmers rotate from the center. Scum is removed from a trough. And here's a picture of the trough of this system. As these go circulate around this way, the sludge is, in this case, oil is pulled into the trough where it is removed from the DAF. These usually have bottom removal systems, and you'll periodically hear somebody talk about a crofter unit. And primarily crofter units are in the paper industry. And I was trying to make a little depiction of what a crofter unit looks like when I remembered this is a picture I took many, many years ago at a paper mill in Mexico. And basically what happens is this spins like a clam. It becomes almost like a clamshell. And it circulates around the unit, gobbling up the sludge the flock that's on the top of the unit. I've only ever seen these in paper mills. I've never seen them anywhere outside of paper mills. But you hear people talk about crofter units, and that's what a crofter unit is, primarily in paper. So now just to talk about the depiction, basic understanding of a circular DAF. The water and air mixture comes into the center. It rises to the top. Here at the top, there are rakes that remove the skim. If there anything settles to the bottom, there usually are rakes in the bottom, which remove the material from the bottom. I do want to talk a little bit about a story at a meat packer I went to, and we were having major problems with carryover out of the DAF unit. No matter what we did, we couldn't control it. Running numerous tests, adding different locations of the polymer and recycle and things along this line, and really had no success whatsoever. And I happened to go to the plant early one day. I was not supposed to be there till later that afternoon, but I came in the plant and the DAF had been drained. And I looked, and somebody had welded a hood over top of the center pipe coming in. And we got a few of the engineers, and we started talking. We were all puzzled because this never really showed up on the drawings. We never knew this was there. So we got to talking, and they immediately were able to remove that top. And it really prevented and alleviated all the problems. Because what was happening, the meat packer had really, actually slaughterhouse, had really just increased the amount of water flow through their plant significantly. And what was happening was, because of this hood right here, this water was coming out and shooting very quickly through the DAF unit, not giving ample time for it to rise. We took this off, and immediately the suspended material, the pin flock coming out of the DAF was alleviated, and everything worked well. But it just came that nobody had any idea how or why somebody would have placed a hood on this, but it was done, and nobody knew it was there. So by just simply opening this up and and removing the restriction, the carryover from the DAF was alleviated. There also are rectangular DAFs. In this case, the skimmers are usually on a chain. And here's a great picture of the chain and the skimmer. And then on here, some have bottom solids removal, And then there's what's called a scum beach. This is the scum beach here and here. And here the sludge is drug up. And there's a better bigger picture of this later. But the water then flows back down, giving you a drier cake, or excuse me, drier sludge on top of your DAF unit. Also, when the water comes into the DAF unit, there's usually a header system down below which evenly distributes the water coming into the DAF unit, creating a nice even sludge blanket on the top. So let's talk about some of the operational controls. We have chemical conditioning in the plant. Is the flock size correct? Is there too much mixing? Is there not enough? Where are the polymer injection points? Where are the air addition points? Where's a good place to feed the products? Where's a good place to feed the air? Then we also need to consider air to solids ratio. Talking with one of my colleagues, he came up, he said that typically he looks for 3 ppm of solids to 1 psi of air pressure coming into the system. So I thought it was a pretty good ratio to consider. But each is designed a little differently, but that's a kind of a good rule of thumb to go to. 3 ppm for 1 psi of air. Other operational concerns: too much flow pushing solids through the system. Clearly, at the at the slaughterhouse meat packer, clearly that's what the problem was. Are there too many solids for the rake to keep up, and not enough solids removal through the system? And is the amount of air not significant to remove the amount of solids you have coming through the system? And for recycles, good rule of thumb is about 30% of the flow, total flow, is recycled back as your recycle rate. Not always, but that's a good rule of thumb that I've seen for recycled DAF units, about 30% of the flow. Some additional operational controls we need to consider: scum blanket control. We're controlling the skimmer speed. If it's too fast, we can get carryover. We can also get wet float rather. If it's too slow, the blanket can sink on us. So let's troubleshoot some of these problems that we potentially could see. High TSS in the effluent, scum or float being too wet, poor lift or float, or air burping. We'll go through each one of these. So if we look at high TSS in the effluent, we always want to change one parameter at a time. And this goes for any kind of wastewater application you're dealing with. I'm as guilty as the next person. I get so excited or something doesn't happen as quickly as I expect, and I'll start changing parameters too quickly. It's always a good change one parameter at a time, see what that does, how it helps you out with anything you're doing. Check your polymer feed. And what I mean by that is I'm a big fan of sampling at various locations. And when I wanted to get to this slide real quick, but on these type units, there's usually numerous places to run and check what the water looks like. But I'm a big fan of taking samples at all different points in the system, looking at it. How does it compare to your jar stir? How does it compare to your jar stir test? Does it look the same? Does it look better? Does it look worse? Will more mixing help? Will more chemical help? So I'm a big fan of checking all the different places that I'm able to within a system and compare it to what I'm getting. Check samples from various points, and that's kind of just what I went through. I'm a big fan of that. Also, try moving the injection points. Do you need more mixing of the flock unit, or do you need more mixing of the coagulant? Was it better to add the air in this location or add the air in that location? And we'll go through some of that here in a bit. This is a biggie. Try injecting the flocculant into the recycle. This has helped me out more times than not in a DAF unit. And let me explain what I'm talking about. So if we think of this red as being the flocculant, long strand of flocculant, which job is to bring these pin flocks together, making them larger for better removal in a DAF unit. So what happens is we bring this together, air comes in and lifts the material to the top of the DAF unit. All well and good, does a nice job. But consider this. Consider when you add your flocculant At the same time, there's air present along with the pin flocks. So what happens is, now you entrap air in the flock, so when it does come into the system, you have your typical air from the bottom, and you get a more quick, faster removal, more efficient removal. I'm a big fan of trying to add flocculant into the recycle. And here's a little better understanding of what I'm talking about. Typically, we're adding our polymers, and that the slide I showed earlier, the little small round DAF unit, they were adding their polymers prior to the air being fed. All right. What I'm suggesting is potentially feeding your flocculant into the recycle line, or after the recycle line, air and water mix together. What happens in this case is you can start entrapping air and particles and flocks together, making for a better rise in your DAF unit. Always check the rake speed. Make sure your sludge blanket isn't too high or your sludge blanket isn't too low. And this is a perfect example of what a sludge blanket should look like. Have some nice craters here that the water can drain out very nicely. I'm going to get into this picture a little later, but this is not a very good sludge blanket, not a good look at all. But we want to make sure that we control and have a good sludge blanket, good drainage, not too much polymer, and this is an excellent look of what a sludge blanket should look like. So let's talk about maybe your sludge blanket being too low. This is a good, just kind of a pictorial example. Here we're having some real nice removal. This is the sludge blanket area in this black here. But let's say that the sludge blanket starts to become too low. What can happen is we can start seeing particles floating out of the back end of your DAF unit, which really causes problems. So you really want to control the height of your sludge blanket. So now let's talk a little bit about your sludge being too high or being too wet. Is your rake speed too fast? Well, back to this same basic drawing. Here we see a nice sludge blanket allowing for water to be released. But here, there's very, very little time for the water to release, and you're pulling a lot of water out if you have a very, very short sludge blanket on your DAF unit. So just something to consider. Obtain drying on the scum beach. This is a picture I showed earlier. A little better example you can see here, the water draining down under the rake, under the squeegee, to allow more water to be removed from out of the scum you're skimming on top of the DAF unit. You might want to try increasing the air to help dry the material out in the float. And here's a pretty radical idea. Try a defoamer. I've seen defoamer used a few times. I remember the first time I saw it was at a plant that made latex. And I was extremely skeptical when I saw it. I was just, you got to be kidding me. But it turned out that by using a defoamer, they were actually able to dry their flock out, their scum out, between 10 and 20%. And we did run some tests, and by golly, it actually worked exactly as they said. So I have seen that. You don't want to feed too much because, obviously you don't want to totally destroy the foam that you're creating. But at the same time, it can be beneficial in drying the scum out on a DAF. As I said, I've seen it. I was a little dumbfounded the first time I saw it, but I've seen it a few times since then. So let's talk a little bit about pour, lift, or float. So you want to, again, consider increasing the air-to-water ratio. Inject your flocculant into the recycle. Again, I'm a big fan of that. Now, another thing to consider is try a higher molecular weight or a higher charge flocculant. Typically a higher charge. What you're trying to do is make a larger particle size. If you're, say, 30% charged anionic, consider looking at a 40%, making it a larger flock. Might give you better mixing, might give you better lift, might give you better air entrapment. Too much polymer can also cause a problem, and it's usually too much flocculant. Remember, I talked about this picture earlier. So obviously you guys can't answer, but when we were showing this picture, we were like, geez, what is that? Well, what that is a reflection off the ceiling of the light. And what's happening here is we have a lot of free water on top of this sludge, which really does not allow for good lift or good removal. And again, this is what it should look like, but look what we're getting. Look, there's hardly any water in the top of here, but here, clearly we can see the light from the ceiling. So just kind of give you a little bit of a depiction. If you are not taking a sufficient amount of sludge off, and you're allowing a lot of sludge to stay in the system, your sludge blanket can continue to grow, causing major problems on your discharge. So it's just something to consider. Again, we really don't want to see that situation in our DAF unit. I want to talk a little bit about air burping. Basically, one of the problems that cause air burping is the distribution head plugging. Now, if we go back to this depiction, you remember showing the header down here for even distribution. If we start seeing pluggage, what happens is it'll start circuiting the water coming in, which then cause large bubbles, uneven distribution on the top, causing problems on the top of the DAF unit, churning the water up, causing potential carryover out of the DAF. Another cause of air burping is in the pressurization tank. And just to give you a little bit of a depiction, I always like to run the water level in the pressurization tank at about halfway. The sight gauge really works nice to tell you exactly where you're at. But if you start to run the level in the pressurization tank too low, what can happen is you can start sucking non-dissolved air, which can cause burping into your DAF unit, causing basic problems. So it's something to consider when you're working on a DAF and you're seeing air burping. It's either from the plugging of a header or from the pressurization tank running too low and sucking air straight through the pressurization tank. So these are just some maintenance tips. You always want to follow the procedures and the maintenance schedules supplied by the manufacturer. Check the operation of the recycle circuit, inspecting the clarity of the water passing through it. Make sure the water is not dirty in your recycle. You want to make sure you have good, clean, treated water coming back through on your recycle in a recycled DAF unit. Conduct and visual inspections of all hydraulic, pneumatic, and chemical feed system. Periodically drain the polymer makedown tank. This prevents any biological buildup or if that can cause breakdown or the wrong dilution rate. You know, if you have an operator that wants to get done early on a Friday and he has to wait till the polymer's at 1 foot, but it's down to 2 foot, let's just do it now. Well, that'll increase the amount of polymer in your system, changing the strength of the dilution. Conversely, if they're working and doing something and they forget and put polymer in instead of at 1 foot when it's almost empty or it is empty, now your dilution strength is considerably less. So make sure you understand and periodically drain the polymer flocculant tank and the coagulant tank if you're making it down to make sure you don't get biological breakdown or you have the correct dilution in both tanks. As needed, drain the scum or the scum trough or area. Make sure that stays clean. Good every now and then to periodically just hose it out. Drain the flotation down to the inlet pipe level. Rinse the inlet header and pressure and try to high pressure the header. Again, trying to keep it clean, trying to keep from uneven distribution. And then lastly, the flotation tank must be raised or cleaned. The inlet socket interior washed and with warm water. And if needed, use an appropriate chemistry to control any biological activity so you don't get bugs building up in your system. So to conclude, we talked about definitions, operation and basic concepts, our basic components and basic designs, chemical treatment, chemical feed and mixing, float removal, operational controls, troubleshooting, few maintenance points, and any questions. If you do have any questions, here is my contact information. Please feel free to contact me with any questions you may have regarding DAFs or any presentation that Brenntag has presented in the past. Thank you for your time. I very much appreciate the opportunity to present this subject matter to everyone. Thank you.